मैं अनुरोध करूंगी चेयरमैन सर से कि प्लाटर देकर सर का स्वागत करें। और हम सब अपनी तालियों के माध्यम से इसमें जुड़ सकते हैं। थैंक यू सो मच। मैं सर को बताना चाहूंगी सर ये बहुत नई पहल है बोर्ड की एंड दिस इज द सेकंड लेक्चर इन द सीरीज। और अब मैं अनुरोध करूंगी चेयरमैन सर से कि वो सत्र की शुरुआत से पहले अपना आशीर्वाद दें। सर।
शांति स्वरूप भटनागर अवार्ड से नवाजित प्रोफेसर and Dr. Sachchidanand Tripathi, who is professor from IIT Kanpur, and all my colleagues. This is the second lecture series initiated by Uttar Pradesh Pollution Control Board, and it has a very good response. All who are seeing it, who are perceiving us, they are appreciating our this initiative. Briefly, just very quickly, I would like to give just few words. Advanced air quality management system. Till now, whatever we are doing, we are also doing the air quality monitoring system in one method. There are other methods also how we can monitor and supervise the air quality monitoring system. In this world, nothing is static. Everything is evolving and everything is changing. Only thing what we are not accepting today, we may accept tomorrow. First and foremost thing, we should listen it. So in that series, we are appreciating what innovations are taking place in our institutions, our academic institutions, research institutions, and in the same series, we have invited Sachchidanand Tripathi ji for delivering this speech, and I request all of my colleagues to patiently listen it and understand what is happening throughout the world, and India is not far behind. Thank you.
Thank you, sir. The theme for today's lecture is data-driven frameworks for advanced air quality management, monitoring, modeling, and decision support system. वैसे तो हम में से बहुत सारे लोग already सच्चिदानंद सर को पहले से जानते हैं, but here I would like to read out a brief profile of sir before we invite him to the floor for the session. Professor Sachchidanand Tripathi is the inaugural Dean of Kotak School of Sustainability at IIT Kanpur and Professor in the Department of Civil Engineering and Department of Sustainable Energy Engineering. Recently been honored with the prestigious Alexander von Hammer Medal 2024, given in recognition for conducting exceptional research in developing regions. In the past,
Okay, first of all, thank you to Dr. R.P. Singh, Chairman of the Pradesh Pollution Control Board, for inviting me to give this second lecture. Certainly, this is a very important initiative. As I said, that is getting some good response. I'm very happy about that he started this initiative, and I know that he said that the world is continuously changing, and be able to adopt that change. I like that idea, what you just said. So with that, let me tell you that some of the work which my group at IIT Kanpur has been doing, and now the group has converted into several centers. One center is Atman, which is basically established under the aegis of Principal Scientific Advisor to Government of India, his office. And then there's a follow-up center, an AI center also has come to IIT Kanpur, which we are leading. So some of the work which are done basically as a part of Atman Center and that AI Center, which is AI Center of Excellence, named as Airawat Research Foundation, and that's what I'm going to present here in next probably 15 minutes or so. I'm sure now this audience knows this, but just to give you some global statistics about these adverse impacts of air pollution. I mean, now you know that there are some landmark studies which tells that air pollution has emerged the single largest killer. We think that there are other diseases that kill people, but now this is air pollution is killing about I think 7 million or something people across the world. And then you see that this data that in India alone, about 2 million people are dying prematurely every year. Every year, 20 lakh people are dying because of air pollution. And of course, then there are other countries which are also picking up. So that is the undisputable fact that air pollution kills people. If you look at that, this is a very interesting thing that these people have tried to collect data from various sources, and they have given this map of PM 2.5 for 2023. So it's a global map. You see that this is scale going from 1 to 80 microgram per meter cube. I know for, and this is, I think, is the annual average. So for India, we are somewhere around 60, because our standard is 60 microgram, but you should know that WHO has made a much stricter standard, which is 15 microgram. Now you see that a couple of hot spots which are clearly, standing out. That you see most of India, I mean, except you see that this white place, which is Kerala and some part of Karnataka, that is all certainly is having PM 2.5 more than probably 30, 40, and many times, this entire Gangetic plain is of course having particulate matter more than 60 microgram or 70 microgram. And then there are some other hot spots. For example, you see in this Gulf area, and then of course some part of Africa also is actually catching up very fast. And I was looking into that when I was going through these slides. I found that because of this forest fire, Canada also has sometimes these hot spots. So natural activities, these kind of like forest fire, because of climate change, is also going to be an important source of pollution, and that we should be wary of that for future. That the forest can, catch up whatever forest we have left, and that can also contribute to air pollution over and above whatever anthropogenic, activities are contributing. Now, this is again a slide just to give an idea that at the global level, what are the sources which are mainly contributing to PM 2.5? So I will just focus on India. So you see there are three kinds of information. It's a little dense slide. You don't have to go through all. But I just want to highlight one thing here, that if you look at India, so major sources are given here in this circle of pi as we call. And good part of that is, if you see, they are shaded like light shade and black color. And this is written here, fuel type. You see, for India, so a lot of pollution, PM 2.5 is coming because of either solid biofuel or from total coal. So we know that coal is used for producing power. Still, it is used for cooking things or for heating the homes, and lots of times people are still using, who don't have access to LPG or cylinders and all, they use solid biofuel, and then that's also burned on roads. So this is an important thing probably for the pollution boards to really look into, and I believe that the new initiative of Campa will definitely do something about it. Now this is something just to give you that how the particulate matter affects human health. So you see, we have a very strong system like a filtration system, just like different now indoor air conditioning and other people are putting these filtration system. Likewise, we have very good filtration which tries to filter particles right here, right? So very big particles like PM10, as you know, they are filtered out. But as the particles start getting smaller and smaller, then as you know, they can be inhaled inside, correct? So PM2.5 can go here, sorry, and PM1 can go even deeper into your through your lung into your bloodstream, and from blood you see it can go into the tissues and then from tissues into the cell and from cell into inner part of the cells. As you see all these details, these are the more medical terms, but the point here is that if they are carrying toxic elements or they are toxic, then of course they are going to harm all these things, and that is why they are causing a variety of diseases. I don't want to go into that, but suffice to say that they can cause inflammation, oxidative stress. People have all kind of issues, and then there are a whole number of those issues that you could see here, right? Now, so these are, of course, to give you that where we are in terms of the global context and what are those adverse impacts. That's what we are looking at here. Now, next probably 10-20 slide, I will focus on that what is currently the monitoring status globally in India and of course in our state. So if you see that, this is a very interesting plot, and it says that how many monitors per million people, how many monitors per 10 lakh people are spread out globally. And you see that, of course, Canada, there are not many people and they have more monitors. They are developed countries. Even US has ping, so they have about 3 to 4 monitors per million. We also have made some progress. All those things will show in the later slide. But globally, you see, we are currently, if you see this dark blue, we are less than 0.2 monitors. Less than 0.2 monitors per 10 lakh people. And as you know, that without saying, that if you can't monitor something, you cannot manage, right? So this is a very well known thing. You monitor your health, you monitor all your health indices. If you have a fever, you monitor fever, right? Just because you want to take antibiotic until you have fever. So just to give an idea, so as of now, we have started to do monitoring, but we are far behind. Even we are way behind than China, which has about, if you see this light blue, which is about 0.7 monitors. So we are 3-4 times less than even what Chinese are. In fact, Chinese are here, sorry. This is even lighter blue, sky blue, which is 1 to 2 monitor. So they are probably have 5 to 10 times more monitors compared to India. Now, of course, if now we focus that at the regional level, what's the PM 2.5 scenario is in India, and what is the population weighted exposure that is in India, what you see that, of course, it again very clearly shows out that these are the states which are basically are most polluted, and followed by some of them which are here, and then of course these are the states which are not still so bad. So these are the statistics which generally are aware with everyone, and we know that generally some agencies or other annually bring out these reports, and many of our cities actually top into the chart, and that is not a very nice thing because it, that it brings the global attention to India that many of the Indian cities are still very polluted, and in many ways this harms the, overall the prestige of the country. Besides harming us, of course, it also harms because then the investments and all other factors, they look into while bringing money to our country, right? Now, if you look at what is the current spread of the monitors in our country, in India, correct? So, what we have tried to do here is that we have given mainly on continuous air quality management system, CAQMS as we call. Of course, we have manual monitors as well, and that number is slightly high. But from Of course, it's a good gold standard measurement, but as you know that generally you get one data a week or sometimes probably two data a week. So for all practical management purposes, this manual monitoring system is not so useful. But of course, it is useful from the point of view of always calibrating and keeping a check of the accuracy of this continuous air quality monitoring station. And what you see that over last 5 to 8 years, during this National Clean Air Program, we have ramped up these CAQMS network across the country. And I think from 150 or something now we have reached to about 562. But any given time, that lives are only 442. And in fact, again, there are some maintenance issues. So probably I will say that 350 or so monitors we get. And that is what, again, that stats is here just to give you again that where we are currently, right? So what we have done that, there are two issues here. That one, that I'm sure that hopefully you are convinced that we need to have monitors, right? Or in other words, we need to monitor. If you don't monitor well, you will not understand how well you are progressing in terms of managing your air, number one. And number two, you want to do that, but is it affordable? So we know that these continuous air quality monitors are expensive. So one system costs about 1 crore plus or little more or less. So this is not scalable, and most of it are basically imported. Now probably one or two have started manufacturing in India, but still the cost is very prohibitive. So you cannot have a scalable solution through this kind of monitors. So what we have started doing that by working with startups and others, we have started basically working with what is called these low-cost alternative to this CAQMS to monitor almost all parameters. Starting with particulate matter, and now slowly we are getting into gases as well. And these are basically, we call them low-cost sensors, sometimes you can just call sensors. And over a period of time, IIT Kanpur has been able to have network to extend several cities in the country, and as was said during introduction that we have also put to a decent size of network in Uttar Pradesh as well as in Bihar. And very recently, I should say that just about a couple of months ago, we put a network in Mumbai in collaboration with Mumbai Municipal Corporation. And now we have also started working with Ahmedabad Municipal Corporation. I will have a slide on mainly on Ahmedabad that I will show at the end. And I should say that this network of sensors, which are in collaboration with several state agencies of Uttar Pradesh as well as Bihar, in collaboration with government, has put 1,380 sensors in these two states by putting one sensor in every block. And these are giving streaming data, all the data is coming to IIT Kanpur, and we are using it for various purposes. And this is all done with support from philanthropy. It is all support from private agencies, and fortunately they have given support to further continue. So this is a very interesting set of data which is going on since 2024. So now we have about 2 years of full data from 1,380 sites, and we are going to continue for at least another 2 years. So I think it's good to know that because you are comparing two different kind of techniques, it's good to know that a technique or a technology which is cost effective, it is low in cost, another which is very high in cost. So how their accuracy and precision, they compare with each other. Like you have a watch, always give this example, that you have a very expensive watch, you know that there are watches which can, give you an accuracy of a second drift in probably 10,000 years. And they cost you how much? 20 lakh. And we all use watches which are 2,000 rupees worth, and they drift every 20, 30 seconds or minute, probably in a month, and we just set it, right? So issue that you have to have some kind of a middle path between cost and accuracy. And ideally what you want to do is that if you somewhat can compare a low cost machine with a high cost machine and improve the accuracy of this low cost machine, then of course you have got a very good solution which is low cost, and if you are building in the country, it is indigenous and it can be scaled, right? Okay, because everyone cannot afford Omega or Rolex kind of watches. But over a period of time, what we will see that everyone wears watches, because now we can always set our watches with some watch which is set with against some other standard, and now that is how we are able to basically do a very good timekeeping. That's the idea what we are going to show it here. So what you see that this is a work, is the first we globally, probably this is the first paper, where we worked with one of our collaborators at Duke University, and we looked at how well PM2.5 works when you measure with a sensor compared to BAM, what is used here in all the monitors across the Uttar Pradesh or across India, right? BAM, we also took another gold standard machine, which Teledyne, which gives even more accurate or well calibrated information about PM 2.5. So you see that these competitions were done at two places, as you see that Duke, which is in US, and you see here Kanpur, which is like Kanpur. And there were two seasons, because in Kanpur, there is a lot of seasonality. You all see that monsoon time, you have very clean air, and then post-monsoon, as the winter starts setting in, you see it's a very dirty air. So we try to look, and Kanpur is the data which I will show you here. And what is shown here is the error. What is the error? So error compared to BAM or Teledyne, which is in a way, let's think like that's a gold standard. And what you see that as you go from blue to red, of course the error goes from low values to high values. And generally we all know that if somewhere something is giving you error about 20, which is in the blue shade, I think we can work with that, right? Because if the cost difference is you see, which I haven't told, the difference in cost is about 50 to 80 times. So in cost of one BAM, you can buy 50 to 80 sensors. So in one BAM where you monitor one place, in same cost, you can monitor 50 or 80 places. And that gives you a lot more data, and that can really help you to do a lot more management, which will basically come in the later part of my talk. So what you see, that mainly for all the purposes, right, where we are monitoring the data 1 hour to 6 hours, that is where you try to manage air quality, correct? All the boards and everything, they look at the diurnal pattern. So primarily they average it over 1 to 6 hours. And you see that during these monsoon time, when the mean values were 36 microgram per meter cube, when actually it was a low concentration environment, there was a little high error. So maybe in yellow, 30 to 35. But as you go for the polluted environment during post-monsoon, that is October, November, December time, you see that for 1 hour and 6 hours, somewhere if you look here, then it has started coming to 10 to 20 or 25%. This was the time when sensors were at a very nascent stage. So that was time basically 2016. This paper came out in 2016. And it is used by US EPA guideline, what they have published, the US main environmental protection agency, mainly for the use of sensors. So then, of course, there are some other details here which I will not go through. So I just want to sum up here that 10 years back, without applying any correction, for high concentration environment, we can give the values within 25 to 30% error. And now, of course, as you will see that with more and more improvisation in the sensors, the values have become only better and better, right? Now, of course, others also then started doing that. This is a work where they looked at in a very similar way by putting a sensor next to a BAM machine, and then started looking at the error or accuracy, whatever you call, and as well as the trend. And they found that if you look at, this is, I believe, Chandigarh, Delhi, Mumbai, Bangalore, and Chennai. You look at that, mostly we have an R square which is ranging from 0.6 or zero point 0.5 to zero point 0.8. And this is also already a 5-year-old study. And there is a good slope. Mostly you see the scatter is also lying around the 1-to-1 line. So across the country, people started taking some sensor, started putting next to band, and they, without doing any correction, they started looking at how these values are looking at. The one thing is there that you need an accurate machine to compare, which is a limitation. You do not have always this luxury to deploy a accurate band kind of a machine next to a sensor. So there has to be a way out, and that's also we discuss in our subsequent slide. This is another work we did, which was again first of its kind globally, where we look into the accuracy of sensors measured by ozone and NOx. Here what we did that we put ozone and NOx sensors in Mumbai as well as in Delhi, and we applied some machine learning model here to correct the value. And after correcting, we found that there was quite a good comparison between that reference, which is blue, in this case it is NO2, and you see that there is a good match across all the days here. And this is for ozone, which is again, the blue is reference and the red is the predicted value. Why do we say predicted? Because the value from sensor was fed into a machine learning model, very simple model, and we found that, well, there is a good comparison between that. So what it shows that even two gas pollutant measurements, NOx, well, NO2 and ozone, can also be corrected, and then after correction, they can very well compare. And now you know that this is the age of AI, so I think easily these kind of corrections can be applied on the measurements made by these sensors. Now, if you look now that I'm going to show you this result, that we put all these Amrit sensors, which were, Amrit is the name of the network which is running across Uttar Pradesh and Bihar. So all the sensors which were deployed in UP and Bihar, which I said earlier that about 1400 sensors, they all were put next to a E-band, which is a very similar device as band. So you see that on the x-axis is E-band, the data from this gold standard, and all the measurements made by sensors. On IIT Kanpur, we call it a test bed. So we have a very well developed test bed where bands are running, sensors are put next to that. We look at the data and we try to see how well they are comparing, and you see there is a fantastic comparison here with R square 0.9, slope is 1.21, and there is a root mean square error is about 50, which is a little bit high. But you see that if you look at the numbers here, probably it was done during winter time, the mean was also very high. So in fact, I asked one of my postdocs recently to do a similar comparison of PM 2.5 sensors which are close to a government monitoring site, and he just showed me 2 days back the data which were obtained from a sensor site in NCR 5 kilometers away and one in Meerut, and I was very, kind of encouraged that R square was coming about 0.8, 0.85. So it seems that, that sensors have, without applying correction, they are giving you data which are quite close to band if the sensors are maintained well. And we know that band also requires a lot of maintenance. So this is one, I think, is a very, I would say that very, very encouraging thing which is happening here. Of course, then we started working a lot on basically how do you use a network information, because as I said that you cannot place a band next to a sensor always. It's very difficult unless you create a mobile laboratory. So what one can do, that one can use the government monitoring network data. So imagine like your sensors, and you also have government monitor data. So there are two kind of networks which are interspersed. So the idea here is that you use this network data and apply machine learning technique to correct your sensor. And that is what we started working on. I will not go too much into the details of it because that will take a lot of time. But the fact is that this is the work we did in Mumbai. And only thing I will try to tell you that if you see here is the reference monitor from Maharashtra Pollution Control Board, the blue line, right? This is the red line, which is LCS, which has differences. There are trends, but these have differences. And Mumbai has the problem of very high relative humidity many times. And once you correct it using one kind of machine learning model, so now this is green, and now you see the green curve, corrected data is very close to blue. So the point I am making here is that sensors have come to certain level of maturity already. So I should point out to Chairman board here, Dr. Ati Singh, that BSI is soon going to publish a complete, what we call that, a standard on sensors. So there are different. So that is where the whole thing has come. I think probably in a month or so, they should publish this. So this is the idea I was telling you that which our group has done a lot of work, that these are sensors of Bihar and these are government monitors of Bihar Pollution Control Board. So this is a very interesting problem for machine learning AI researcher. We have worked with many AI professors of IT Kanpur. So what you do that, you use this data, that is all shown the details here, and then you try to basically correct the system. So all these are becoming increasingly possible to kind of do the bias correction easily from the data which are available in the field, instead to have the need to bring always the government monitor or the gold standard code reasons. So I'll skip this here. Now another thing which is a very interesting problem is that what we did in Gujarat for Surat city is how do you optimize the size of a network? And this is the problem I think the board and UP Campa will have soon, because they are going to deploy 200 government monitor, and let's say they want to augment it with some sensors network. Now the question here is that how many government monitor you put in a city to have adequate sampling that satisfies the system? Why are we doing all this monitoring? Basically, we want to protect the health of people because we want to protect the environment. Correct? So, who needs to be satisfied? The eventual goal of the government and the board is to basically meet the citizen satisfaction. Correct? So, that is what we used here. So, the problem here is a very good, interesting optimization problem, which says that you have this much of money and you have certain constraint. What kind of constraint? I can give you some example. That if there are schools, so always the schools will like to monitor because there are kids there, and kids are more susceptible or vulnerable to basically air pollution. Or if there are hospitals or old age homes, so you want to certainly have a monitor there. Or there are very big crossings. For example, here the Alabama. You know that all of us when we cross, we get stuck there for 10-15 minutes. And if you are on a motorbike, then you are sampling a lot compared to other places. So there has to be monitored, correct? So these are constant. So even that you have a limited amount of money, how much you spend on, let's say, putting government monitor and on sensor, and where do you place it? And such that citizens feel that the air they are breathing is being monitored adequately, correct? That's the problem. And we looked at this problem using two algorithms. One is called genetic algorithm, and another is called a greedy algorithm. They are very well established algorithms. We again collaborated with my department, optimization experts, and some very interesting results. So this again is something which is a part of now guidebook, and it is there for people to use. It gives you a very objective way to design a network in a city or in a state or in a commissionerate, rather than having a very subjective way to design a network, right? So this is what, I think this is a PDF now, but so that's why it's not coming well. This is your Amrit network. You see that all these red dots are basically showing the government monitor, right? It's shown the government monitors. I think UP has about 60, Bihar has 35, and these all blue dots are basically the sensors what we have put across these two states. So you see that now, there is enough data coming at least to understand that what is the current state of air in rural part of the states. Because I think all the board people sitting here, and they all know that all of these monitors are basically based in cities. That's part number one. So it's a very city-centric network currently we have, very city-centric. Now, second thing what you see, that in UP, if you look from, I think, eastern part of NCR to Kanpur, there is no monitor. You see that, right? Then you go here, from Kanpur and right, entire central part, there is no monitor, right? Here. Look at that. You go up to Madhya Pradesh, there is no monitor. So basically, you see that there is a very sparse, inadequate monitoring going on. Right? So even if you add 200, which is a very good step by the way, that 200 monitors you add, UP has 75 districts. Still, you will be able to, on a, let's say, if you do an equal distribution, you will have 75, 2.5 monitor per district. It is not enough. So therefore, we need to look for other kind of alternate way to generate data. And why there is a need of data, I will tell you in subsequent slides. Right? So there is one interesting outcome that came out from this work, which was published in a top journal, Environmental Science and Technology, only a couple of months back with my postdocs, is that we created first data-driven, using AI, the airshed demarcation in Bihar. So you see that with the network spread across Bihar, we were able to get how many airsheds are there in Bihar? 1, 2, 3, 4, 5. Right? And as you know, some of you know that this is an idea which is an emerging idea, a good idea, that you try to manage air on the basis of airshed instead of on the basis of the administrative unit. Because air sees no boundary, as you all know. So to manage air on the basis of a district or a division or commissionerate or on a state will serve less purpose compared to when you basically manage it on the basis of airshed. Okay, and that gives you, in a way, to cooperate and while conserving resources. So I will give you a good example here. So you see that generally one airshed has about 5 to 10 districts. So that what it actually, in a way, it fosters is a cooperative approach between districts. They can share the data, they can find out which district is causing to pollute other districts, etc. And this will become very clear if I show you this plot here, that there is just a new result which has come out, and it is airshed across UP and Bihar, right? And now you see that there is this airshed, which is this color, like I think is a little bit, I think brownish color, and there is one, this is purple, right? Two colors, all of you can see. And these airshed are extending from Bihar to UP. You see that? That means they really need, if they want to solve the problem of this region here and here. I see there's a really very nice boundary for some reason. We are still looking into that. They need to cooperate. That Eastern UP need to cooperate with Western Bihar on both north and south side of it. Right? This is what we are talking about here. So if they cooperate, they can have much larger success in managing air of this whole area. Likewise, you see that we all talk about that NCR always gets polluted. This, I am not doing that. This is the data is giving us. Look, entire NCR has come out. It's a very nice airshed. Right? And see, so all these needs to be looked at together. You see that it's almost like entire NCR. So these are all the data itself has told us by applying AI. There is nothing we have done. This is one of this kind of work we have done. Another very interesting thing which I want to show you, as I said that, do you think the rural people have different lungs? No, right? They are equally affected. But have we been monitoring rural air quality? Not at all. So this is what Amrit has been able to achieve, you see, and something which are very exciting here, that the common perception that rural air quality is better is no longer true in Bihar. That is what we have found in Bihar, that I think airshed 1, 2, 3 is in UP or Bihar. I forgot that, but looks like that it is Bihar probably. If you look at here, that look, this is the rural, right? Rural area. So we looked at the Government of India settlement type, and by that we mapped blocks into different settlement type, and we found that this Bihar In Bihar, you see that in one airshed, rural PM 2.5 is larger than town and urban. And there is a reason for that. We have done a modeling work, and that clearly shows that why this is happening. Because we all know that LPG penetration is way lesser in Bihar compared to all other states in the country. So the rural Bihar is still consuming a lot of solid fuel, and that's why rural air quality in Bihar is far poorer than the urban Bihar. And then there are some lots of other interesting results. One more thing what we have done using these kind of dense network is, and then again using AI, is to predict PM 2.5 concentration from block level measurement to the village level measurement. So imagine that earlier I said that we have this monitoring going on in 530 blocks in Bihar, and how many monitors were there? Government monitors were about 35. So from 35 we made it up to 500 plus sensors. Then using AI, we are able to predict PM 2.5 at village level, and there are thousands of villages in Bihar. So now this is the data what we are showing here at the village level. That at village level we can see what is PM 2.5, and then we can associate with the people's age and different their socio-economic status, etc., etc. And that can really give you a very good idea that how people's health are getting affected. And that will help. In fact, we are using this data and working with several economists to design interventions in Bihar as I speak. That we are working now that what are the best way, most optimized way, effective way to intervene in the Bihar, mainly in the household sector of Bihar, to cut down the emissions from the household sector. Right? I will skip this. This is another interesting thing I should show because we are all in Lucknow. You will find it very interesting. So we all know that Lucknow, the board has about 5 or 6 monitors, correct? And Lucknow has an area is about 900 or 800 square kilometers. So you are getting one data point in every 150 square kilometers, right? This is a too less of data to do effective air quality management. So what we have done here, actually, as a part of a project, we installed about 70 sensors. All these dots are sensors. So we installed 70 sensors in Lucknow. And we also use satellite imagery. So you see that these are the images taken by these satellites, and you all know that satellites are giving us better and more clear images. Some of them are free, some of them you can buy, but they are very cheap. And this is what the machine learning is allowed or enabling us to do. For example, you see that this is a dusty day over Lucknow, somewhere in Lucknow, and this is a clean day. You see the difference. Now this can be extracted by machine learning model and can be trained by this large number of sensors, which are already calibrated using government monitors. You see that? So which is brought on par with government monitor, and then you develop a complete machine learning model pipeline to predict PM 2.5 at the scale of half square kilometer over Lucknow. You see that this is all map of Lucknow. I'm showing summer and winter, and this is each of these blocks. You see the tile is a half square kilometer. So from 6 data, 6 government monitor, now using satellite images, sensors, and machine learning model, we are able to predict with an error of only 24%, which is not large. When you are sampling 120 microgram per meter cube, whether it's 100 or 150, it doesn't make a difference. You are still not close to 60. So, and now actually this model is able to give us even accurate result. Over Bihar, we are able to do with an accuracy of basically 85%. So error has been dropped even from 25 to 15%. So you see that this is all I believe is the Hazratganj. And you see that now if you get information at half square kilometer, 1800 data point, every day you can generate over the day. You can map it that what's happening, or is a Calcutta, or there's a brick lane here. So very simple that using this kind of data, you can simply overlay with source streets I'm going to show, and then you can find out that what to do. Right? That's one way to work on. Another way is that what we have also developed a mobile platform. So this is what you see is a laboratory on wheel as we call, like you have seen sometimes food on wheel, train is there, which is I think a transporter on a wheel. This is a laboratory on wheel. What you do that it is a laboratory with instruments which are little more sophisticated with the regulatory monitors. It has mass spectrometer, etc. etc. It can sample anytime. You can take it anywhere and you can plug and it starts. So all you do just, if you are going to a new place, you have to calibrate it, it takes a day and next day starts sampling. So in fact, in Lucknow we have done using this mobile laboratory. We have done it over 5 locations over 3 seasons. So overall about 14 deployments we did with this mobile laboratory and we got some very interesting results. You just see that here. That look at Tal Pagoda, which we all know is industrial site. You look at only metal, only elemental part of PM2.5, 37.45 microgram or 37. And look at this site, which is forest impacted or forested site, is CSR, that laboratory is 5 microgram per meter. And then of course you see all these details, these are all you see elements. Sulfur, potassium, silica, iron, calcium, and all that is there. Correct? And this data you can get from every site in only 10 to 12 days. Okay? And you can use that, run the model. It's a very well established technique. Okay, and has become very, very accurate over a period of time. And you can see that, for example, look at again Tal Pagoda and this site, which is the forested site. You see? Something is happening. Of course, this is because of firework. Maybe it's for Diwali time. See how well it's taking the Diwali signal. Other times, let's look at that here. Right? Look at this. This is not the Diwali time. Something else is happening. What is happening here? This is green, non-exhaust, and this one is something like some other color, coal combustion, something of that sort. So you see that lots of information we can get with a very short deployment of about 12 to 13 days that what sources are operating at that place there. So what we have done, we have again brought this machine learning strength. We have combined the mobile laboratory and sensor data with machine learning to provide source apportionment almost on a continuous basis. This is forming now one of the, you can say, the layer of our decision support system. Correct? We all know that what way currently we do the source apportionment. We take a sampler, we put it somewhere. At least we collect 100 filters, which takes minimum 100 days. Then you bring to laboratory, you analyze, and that takes another probably few months, and you wait for 5 sites. So it takes 1 to 1.5 years, probably at the least, to give you source information. This is what we are saying here, that this information at one place, we got it in 14 days. 12 days mobile laboratory, 1 day for calibration, 11 days of data. You run the model, you get the source. Now mobile laboratory of course is expensive because it has, I said, many expensive instruments. So what we are saying, we are combining this with sensors and machine learning. We have trained machine learning model and we have the sensor package there which is giving us particulate matter and gases. Combining these two, we are giving source information very well. So this is the idea that you take the mobile laboratory, keep it stationary for 12 days at the site where sensors are running, you train the data. Now after the mobile laboratory has moved, but the sensors which are trained with a machine learning model will keep on giving source apportionment. Reasonably accurate. You see that here? There are 2 sources I am showing. One is a biomass, another is a urban source. And you see there is one actual which is given by the mobile laboratory, which has all the best instruments and it gives very accurate result. And another is basically predicted using sensor data and machine learning model. You see that they are very close. Even traffic, look at traffic. They are so close to each other. Just imagine that for the regulators, if you get this information over Lucknow at 20 places in real time, you can do something in time, instead of waiting the information to come after a year or something, or based on only emission inventory. So that information is also important. But this information can really help you to mitigate some sources which operate on daily basis. If there's a burning on road, if somebody has not complied with the C&D waste disposal, or there is a traffic congestion. So traffic congestion you can really manage in time with these kind of. I'll just skip it here. So in fact, lots of these sensors earlier have been imported because only China was building. Now, as a part of our center, our team has now built this sensor. See that this is a sensor, and you see this is a credit card. So this tiny sensor now is all mostly done, and hopefully a totally indigenous sensor will be in the, I think, there for everyone to use probably in 6 to 8 months. Right? I will skip it here because this is more combining heat and pollution. This is a problem we are working on. I will not probably go into that because of lack of time. So this I will come straight away to this decision support system, which now the AICOE has developed. So how it works? So as you see that it has multiple layers. You see there are government monitoring network. I showed this image in the very beginning. Right? So this is all the government monitor across the country or across, let's say, the village. And then you have this sensor network, and I have not shown here. You have these satellite images which are coming. You can put land cover, which ISRO is giving us for free at a very high resolution, at a resolution of 2 meters. That's another layer. And now you see AI models using this multiple data is giving you the airshed. It's giving you, like I showed for Lucknow and Bihar, this hotspot, and it's further giving you the sources. It's not only giving you the pulse spike, it's also giving you, I did not show that, this time series, that every hour, if there is a spike, if there is a spike in PM, is it a spike because of a sudden congestion on a road, or some burning has happened, or something else is happening, you can clearly correlate all these time series are time series for sources. So that is what we are currently working on. Well, I mean, it's almost done. So the way it does, you see that it has all these ingredients to really have a very robust decision support system. You see that it looks at basically it's an intelligent platform. It can do airshed analysis. It can give you source apportionment, and then it can trigger that who is actually responsible to act on it. Is it someone from municipal corporation or from board? And when they log in, they can see what is the issue here, and they can actually take some action. And after that, they can also see what is the effect of their action. So all that is possible, and that allows you for in-time intervention. And after that, because it is all data-driven, you can also look at it that once you have tried to decongest the road, whether that spike has gone up. So that is what we are currently just trying to deploy that in Lucknow. So from middle of June, this whole thing will be running in Lucknow and as well as in Kanpur, where we are putting, in addition to this UP-wide network, 125 sensors in each city. In Lucknow and in Kanpur, and this entire decision support system will be running. And of course, there might be some error in each of these predictions. But the fight is that, as you all use now, some of you might be using ChatGPT and etc. You see, by all these interactions with people, by their accurate answer, all the wrong answer is corrected. So every version is getting more and more accurate, and that is what we are trying to put in here. I will skip it here. I will say that this is our new deployment, which is very interesting, that Ahmedabad Municipal Corporation, which is hosting, Ahmedabad city is hosting the Commonwealth Games, which is one of the prestigious global sports event in 2030. And they really want Ahmedabad to have, well, at least Indian standard compliant there, right? So it should meet at least on daily basis PM 2.5 plus 60 microgram per meter cube. So they are taking our help. We have a formal agreement with them. We are going to have a sensor network deployed there and our mobile laboratories there. We are doing a baseline survey, and I guess that this complete decision support system should be operational there probably in 1 to 1.5 years. This is what currently the mobile laboratory you see. In 2 days, it just reached Ahmedabad and is currently doing sampling technique. Okay, so with this, I thank you again and thanks for your attention. If there are some questions, I will let you know.
Sir, any question? Right.
Thank you so much, sir, for a very insightful and enriching lecture. Anybody has questions आप पूछ सकते हैं सर से. अगर किसी को कोई सवाल हो.
Sir, thanks for such an insightful lecture. Sir, just 3 points, sir. All this while there's been this hue and cry on this smart sensors, primarily because we were using it as a standalone unit. But once you bring this network concept and air concept, modulation concept into the picture, a lot of that is circumvented. But sir, there are a couple of things. One is RH, which impacts the quality of sensors to an extent. And secondly, when we talk about NAQS 2009, they have already specified the measurement techniques. So how do we circumvent those two aspects in this case?
So see, this is working right. So temperature has little effect,
Exactly, RH, sir.
but RH also see in India, well, Uttar Pradesh, let's say focus, like Mumbai or coastal regions, RH exceeds 70 or 80%, where PM actually start responding very abruptly. But what happens that what PM does is crystal. Like think about the salt, it's a PM, right? Salt particle.
It becomes colloidal, basically.
Yeah. So, well, yeah, more and more collateral. You're right. So more and more water it will grab and then it will grow. Correct. And more it grabs, then it will start overestimating because now it's a drop, right? But UP, you see that the main problem is only for 2 or 3 months where high RH is there. Correct. Starting from 25th June and maybe not even October, I would say early September. Correct. But that time PM is so low. If you look at that, because if you have a good rainfall, any time good rainfall happens over a spell, right, 3-4 days, lots of things are washed out. So PM is low, but despite that, if you have temperature measurement going on, which are inbuilt in these sensors, you can correct it. When I say that from 16 to 2026, that the overall accuracy of sensors have really dramatically increased, both in terms of not only precision and accuracy, but even the overall amount of maintenance that is required for these sensors, right? So for very humid, like so what we are doing in currently in Mumbai project, which is MANAS, Mumbai Advanced, what is that? Mumbai Air Network for Advanced Sciences. That is specifically looks for RH controlled sensors because in Mumbai,
Is a different working
yeah, it starts from April high RH starts and then it goes all the way up to end of September, etc. So there we are looking for RH controller for UP, except some part of the fog time, maybe middle December to early January or end of December to middle of January, and then as we talked about monsoon, and that also. Whenever you have dry period, there wouldn't be issue, when the monsoon recedes, correct? So wet period, but that is amazing. I mean, you come sometime, we'll show you that this RH corrections can be done because you have those measurements going on together. So, but the fact is that, you are getting more data. So the more data is allowing you to, that is giving you so much of power to decide, design and intervene. You see, the major problem what we have today, that we decide, let's say that first problem is that we are not able to decide because we have lack of information. You are able to decide, you are not able to design the intervention. You know the intervention, but where and when? So what this decision support system can tell you, you find suddenly, let's say there is a dust spike. So dust, you have dust sweeper, mechanical sweeper. But how many sweeper Lucknow has? 5, 10, 20. You will not have 1,000 sweepers, mechanical sweeper in Lucknow, correct? One sweeper costs you 1 crore, right? So there is a limit you can buy. But where do you deploy it in time? That's the thing. That where there is a spike of dust, you deploy it here, that's the thing. Correct? Where there is a real some smoke is there and you deploy anti-smog gun. Right? So very effective deployment in time is the key. For example, I talked about this household pollution. Now, there was this Ujjwala scheme. It was reasonably successful. I mean, it has good success. But people started withdrawing and the subsidy was withdrawn, all that happened. Now see, all these information can now tell you which are the pockets. There are many pockets where people are not able to afford. But they are the ones which probably are driving their pollution in the city. Correct? So now you have to look at it, the cost and benefit analysis of it, right? That do you gain by having the subsidized connection to those poor households? If you can bring down their pollution substantially, right? So all these things, this possibility emerges. And you know that this error correction is just becoming more better and better just because of the way AI is progressing.
So coming to anti-smokers, as you mentioned, since RH is playing such an important role, is anti-smoker actually helping?
No, I mean, I have seen one study which is Dr. Sagni Day at IIT. He looked into that. So what his study I think says that close to road, very close to road, it does.
But if you
not beyond road, I mean close to road. Yes,
and if you do it from a height, it again.
Yeah, so I have not looked into that detail, so I will not comment on that. But the point is that issue that you have anti-smog gun, right? And you have mechanical sweepers, overall utility is questionable, correct? But issues that you have them, how do you use them effectively?
That's it. So
correct. So that is yes, when and how. So some things, of course, will require a different level of consideration. There also these kind of decision support system will help you. But some things which you can do, see, for example, now we know that 4 o'clock or 3 o'clock, this road always has a pollution. Now, but there are other roads which are actually, bifurcating just before the red light when the road starts, correct? So if you have a real time that information coming, you have the real time CCTV footage coming. So you know the traffic flow. And now you are seeing that, well, there is so much spike going on. You can, just divert the traffic. I mean, there's so many things. This is what actually the smart city is all about, right?
The second is regarding the AOD. So during winters, when there's so much accumulation at the inversion layer, when there's too much accumulation at the inversion layer, is AOD reliable during that period as well?
See, AOD as a only feature for models or parameter, whatever you call. Now for AI you call feature, otherwise you used to call it parameter. Has problem because it's a columnar thing, and as you say that where the aerosols are in the column can be a major problem. It's not really what you are breathing like, what sensors or PM or the BAM is measuring, right? But AOD, despite its error or biases, can be a useful now parameter we are thinking to put in our AI.
When integrated with some other.
Absolutely. These are common. So see, as you said, integrated approach with a multimodal data. The government monitor, the satellite images, the optical depth, the sensor data, but you need to have sufficient coverage on ground. Then only you will be able to have enough ways to correlate and correct all these space bond and other kind of.
So the last question is on DSS. In DSS, the meteorology plays a major role because whatever DSS you are forecasting, it is primarily based on the meteorological parameters. So in this, whatever schemes of things we have planned, from where are we taking this meteorological data? Is it from reliable IMD sources or you have your own solar system?
All from IMD. Okay. IMD, interestingly, MOE's secretary visited us, I think 1.5 or 1 month ago. So he's the top boss of weather, right? MOE's secretary. And we knew that they operate, but they said that for agriculture departments, they have got thousands of these weather sensors installed across the country, and all of that data is going to IMD.
We have just got access to the data. In fact, in Lucknow and Kanpur, we are integrating this with. So we are not only saying that this is the source which is causing. I forgot to add that. By integrating the wind speed and wind direction, we are able to tell what is the probable location of the source, and we are also working currently that what's the timing of this. So AMD has data. Just kind of bringing more data into the layer, and you always have this flexibility to add more data layer. That's what we are working on.
Thank you. Thank you, sir. Thank you.
So, this your sensor-based model, there is a resistance from the government. Why not IT or research institute should define some other parameter in place of AQI? Whether you are thinking on that, some support system index for the
That's a good idea. Good thought.
yes, one day once the person will install us says to the same line.
Right.
Since it's useful,
Right.
why not there should some work should be done? Since it's good for management, air quality management.
You're saying that just like, if I understand you correctly, that we said air management, California is a kind of pioneer state in air management. They said California air resource.
Yes.
So they said air is a resource. Is it something of that sort you are saying that change that, right?
That acceptability will be drastically increased, and there will not be any clash.
We'll discuss more with you about that.
And second, once you have a good network in UP, where this is being displayed,
This all comes to IT campus server.
IT campus.
And we are just working on to make all these data live. It's a part of the, I think last year you were there when in Lucknow, correct? That person from the philanthropy was there and he said that all data has to go. So we are making all these data now public as this is part of the agreement. So there will be live dashboard. There will be live dashboard for Atman Center, but for AICUE, which is from Government of India,
Okay.
that's a section 8.
So right now we are not sharing with the government. Any government agency
Selling
sharing.
this data, no, Bihar government has taken all the same, all.
Mumbai urban development is taking this data, not other.
No.
So that is
But Mukesh is here. That the network we are setting in Lucknow and Kanpur.
Yeah.
So Kanpur Corporation is going to use it as a part of their smart city. The whole, we have MOU Kanpur smart city, and they are the whole decision support system is designed as per their requirement. So that what will be running from July in Kanpur will be probably be used by the Kanpur smart city.
Since what CAQMS system definitely in another 30-40 years we are not going to expend so much and creating such a robust network. So it's definitely sensor-based network had to be used for management, air quality management. But in what way that is to be seen?
Yes.
And that. Okay, thank you.
Thank you, sir. Any other question? Thank you so much, sir. It was indeed a very insightful, enriching lecture. For the formal vote of thanks, I request Ram Gopal sir to please deliver the formal vote of thanks.
हेलो आदरणीय अध्यक्ष महोदय एवं कार्यक्रम के मुख्य वक्ता प्रोफेसर सच्चिदानंद त्रिपाठी जी एवं सभागार में उपस्थित सभी अधिकारी एवं कर्मचारी, डाटा डेविएशन फ्रेमवर्क फॉर एडवांस एयर क्वालिटी मैनेजमेंट विषय पर आयोजित इस महत्वपूर्ण कार्यक्रम के सफल आयोजन के उपरांत में हृदय की गहराई से सभी की प्रति धन्यवाद ज्ञापित करता हूं। आज के इस कार्यक्रम में वायु गुणवत्ता प्रबंधन, डेटा विश्लेषण, आधुनिक तकनीकी एवं पर्यावरण संरक्षण से जुड़े महत्वपूर्ण विचारों और अनुभवों का आदान प्रदान हुआ। श्री त्रिपाठी जी के ज्ञानवर्धक एवं अध्यक्ष महोदय के सुझावों ने इस विषय को और अधिक प्रभावी एवं उपयोगी बनाया। मैं विशेष रूप से अध्यक्ष महोदय एवं प्रोफेसर त्रिपाठी जी का आभार व्यक्त करता हूं, जिन्होंने अपने बहुमूल्य समय एवं अनुभव से हम सभी को मार्गदर्शन प्रदान किया। साथ ही आयोजन समिति, तकनीकी एवं सभी सहयोगियों का धन्यवाद करता हूं, जिनके अथक प्रयास एवं कार्यक्रम सफलतापूर्वक संपन्न हुआ। आशा है कि आज की यह चर्चा स्वच्छ वायु एवं बेहतर पर्यावरण की दिशा में नए विचारों और प्रभावी कार्यक्रमों को प्रेरित करेगी। लेकिन ये कार्यक्रम के समापन से पहले मैंने एक छोटी सी कविता बनाई है और उस कविता में जो हमारे मुख्य वक्ता प्रोफेसर सच्चिदानंद त्रिपाठी जी ने जो विस्तार से 1.5 घंटे में हमको जो बताया है, उसको मैंने कविता के माध्यम से लिखा है। हवा की इस लहर में छुपा है एक संदेश, डेटा की भाषा समझो वही बने परदेश। कहीं धुआं, कहीं धूल, कहीं जहर का प्रवाह, फ्रेमवर्क बताते हैं कहाँ रुकेगी आप। डेविएशन जब बढ़ता है संकेत देता है साफ, प्रदूषण की चाल को विज्ञान करे नाम। सेंसर की आंखों से शहरों का हाल मिले, हर आंकड़े के पीछे जीवन के सवाल मिले। एडवांस मैनेजमेंट का उद्देश्य यही महान, स्वच्छ वायु हर जन को मिले, सदा मिले सम्मान। डेटा बने प्रहरी, जब नीति बने मजबूत, धरती फिर मुस्कुराएगी, होगा हरियाली रूप। एआई और विज्ञान संग प्रकृति का हो मेल, हर सांस सुरक्षित हो यही सभी का खेल। राम गोपाल कहते हैं ज्ञान और पर्यावरण का हो ऐसा अभिमान, ज्ञान और पर्यावरण का हो ऐसा अभियान, स्वच्छ हवा की ओर बढ़े भारत का हर इंसान।
Thank you so much, sir. And with this, I think we come to the end of this evening. अगले महीने एक नए विषय पर एक नए एक्सपर्ट के साथ हम लोग फिर यहाँ एकत्रित होंगे। तब तक के लिए आपका बहुत बहुत धन्यवाद।